The wave does not collapse. There, that's like half the video. You can just skip it if you want. Hello everyone. This is the follow-up video that I promised I'd do after chapter 6, which was on the true nature of the photon. So it should go without saying, this video makes no sense unless you've watched that one. If you leave a comment on this video and it is very clear that you haven't watched that one first, I will ignore and or make fun of you. Good? All right, moving on. So the biggest question that I got from my last video were a lot of questions kind of around the same thing. If the photon is actually more of a ring, when the ring hits an electron and creates interaction, does the rest of the ring disappear? Is it like a balloon that pops? What happens to all that energy? And if it doesn't pop, if it doesn't go away and it just keeps expanding, how do we conserve energy? So that's going to be the main focus of this video. And then we'll kind of do a rapid fire a little more after we get through that. But before we dive into all of this, I want to start with a mental picture, a concept that I want you to kind of have in your mind. And at the end of the video, we'll come back to it. So here it is. So of course, I'm an elder millennial, which means I knew what it was to have a childhood without the internet or iPads. And one of the distinct memories people my age or older share is the day that we found out you can start a fire with a magnifying glass. It was a wonderful day because most of us had a magnifying glass, if not they were cheap to get, and our parents figured they were probably a safe toy for us to have. Maybe we got in a science kit for Christmas. And then all of a sudden, you come home and you think to yourself, I have a weapon. It's a beautiful thing. And we all rush out the day that we found this out, and we try burning a leaf, burning a blade of grass, just seeing what we could do, burning an ant, for those of you who are sociopaths, and just see what we could do with the magnifying glass. So here's the picture or the concept I just want you to carry as we discuss this video. As you hold that magnifying glass, trying to find that perfect position with the sun, where the magnifying glass makes this little point of light, and you start seeing the little steam or smoke kind of begin to form, our first thought is that the light is causing the heat. The light we see, the bright dot, is what's causing all that heat to form. But here's the thing, once you start understanding how this world works, it's not the light you see that causes the heat, because the light you see is already being handled by the interactions with electrons that re-emit the photons back to your eyes. The heat is actually caused by all the light you don't see. And that's one of the most amazing things to have click in your mind as you're trying to understand this world of, the subatomic world, the world of EM waves, world of photons, all this stuff. The relationship between energy conservation, photon interactions, light, all these things. The light you don't see is what burns the leaf. The light you see doesn't. All right, so back to the question at hand. If the photon is a ring, and as that ring expands and it hits an electron and we form, again, those interactions that we call photons, what happens to the rest of the ring? Does it pop? Does it go away? No, it doesn't. And when I was doing my research on this, that was the first question I had. And as I've mentioned before, I've been privileged enough to get help with this video from people in the field, actual optic engineers, and we'll hear from one of them later. This is a question I asked, and we thought of a lot of different experiments. Like, has anyone ever questioned this? Has anyone thought of this? How do we confirm? How do we answer this? And the answer came back, light is just too small for us to confirm certain behavior right now. even if we could measure it, the equipment is too expensive outside of any of our reaches. So the thinking was, light's too small to really test this with, but radio waves aren't, and radio waves and light are the same thing. They're both EM waves. They represent different interactions, but they are the same thing. So let's just test this with radio waves instead of light waves and see if the bubble pops. So here's what we did. And feel free to do this at home. We created a giant, basically Faraday cage. We used military-grade Faraday fabric. We covered a very large box. And closer to one side of the box, we have a broadcasting antenna sticking into the box. And on the other side of the box, we have a radio receiver, because you have to create this perfectly closed environment. So how do you know if the radio is getting a signal? Well, if it's an actual radio, it plays sound. So we had a radio transmitter, we had a radio receiver. The radio receiver inside of the box was farther away from the broadcast antenna than the radio outside of the box, which was very close to the broadcast antenna but blocked by the Faraday fabric. And basically, what we wanted to ask ourselves was, a radio wave is also an expanding sphere. So if we start broadcasting the radio wave, and the radio wave is, put this in quotation marks for now, absorbed by the Faraday fabric or blocked before it reaches the radio on one side, if these EM waves are a bubble and they give all their energy away with one interaction, then the radio wave should pop before it reaches the radio on the other side, and we should hear no sound. We shouldn't be able to pick up the broadcast. But sure enough, no matter what we did, the other radio still picks up the broadcast. As long as there is a clear line of sight to the other radio, it picked it up. Now, I don't want to spend a ton of time on this, because we ended up not recording this for the video, but this is something you can do at home. And a lot of the caveats you may be thinking of, just feel free to test for yourself. For example, how do you know the Faraday cage isn't just bouncing the radio waves back on one side and it's not absorbing any? Well, you can test that because there are gadgets you can buy that will detect the strength of the EM waves passing by it. So you can get equipment to actually test and see, okay, if I have the Faraday cage present, am I getting both the wave and the reflected wave, or am I just getting the energy level of the original as it's coming by? You can do energy comparisons inside and outside of the box. And actually, I recommend playing around with Faraday cages and radios. It was kind of fun. Now, that's not the only reason that I became convinced the ring doesn't pop. We have more reasons, but we're going to have to jump around a little bit, so stay with me. So just let's assume for now the ring doesn't pop. As a photon ring expands and it interacts with an electron, and that starts producing our photon interaction, the rest of the EM wave just keeps going. How does that not create a situation where there's infinite energy? And how do we conserve energy? Well, this is really fun and it's really deep, and I'm going to touch on it just deep enough, hopefully, to satisfy your curiosity. But to do that, I have to answer another question at the same time. And that has to do with locality. This goes back to our nonlinear crystal. One of the pieces of evidence I gave for the photon ring is nonlinear crystals. And again, this is the idea that there are crystals that we have found where you can shoot a stream of photons into it, and a small percentage of those photons split into two photons, each with half the frequency of the original stream. Again, I consider this strong evidence because there is no other explanation for this behavior. In fact, it completely contradicts our current understanding of the photon, thinking of a photon as a particle at all. But it works perfectly with photon being a wave with a ring of potential interactions. That ring, as it expands, hits two electrons at the exact same time. And then I said, but because two electrons are responding to the same imbalance in the field at the same time, the acceleration is slowed, much in the same way that if you push a box with a certain amount of force, it will go speed x. But if you have to move 2 times those boxes with the same amount of force, now it's going to slow down. I just realized that Taz fell down. Sorry, everyone. So a lot of you now asked another question. It's a great question. Wait a minute. If both those electrons are responding to the field at the same time, and that's somehow cutting the amount of energy in half for the other, now am I insinuating some kind of instant communication between these two electrons? Again, no. So we're going to dive in deep here. This will get a little weird. What I have for you first is an animation. And what we've done is we've set up a theoretical circumstance where we're showing it visually. An emitting electron and 2 electrons all equally spaced apart. And you can see also that we are using wavelengths at equal lengths on each side. What we've done is we've color-coded these so that blue represents, the wave going up, red represents going down. And as you can see in this animation, in this triangle form, as the electrons interact with the light wave, they're going to do what we know electrons do. They interact with an inverted wave because, again, when the electric field moves one way from an emitting electron, the receiving electron is going to move inversely to that. That's why light cancels out with backpropagation, because when the receiving electron reacts to the wave it gets, it moves in reverse. So these 2 electrons, they receive the waves, and as they receive the waves, they respond by moving inverted to that. And now their inverted motion goes towards each other. And once that reaches each other, it is timed with the original emitting wave, and it starts canceling out parts of the wave. And what you can see from our animation here is that the end result is we get half the frequency. Am I saying this is what's going on in a nonlinear crystal? No, it isn't. At the moment, this is a thought experiment, and we showed it to you because it's the simplest version of it. Here's the problem with this. We get kind of half the frequency. The problem is we don't get half the wavelength. So yes, it's creating, the wave is moving with half the frequency, but it's more like a heartbeat. It'd be like a really fast strobe light. So it's not actually what we're observing from nonlinear crystals. So that can't be the answer. Here's the problem. Light waves are a whole lot longer than the distance between 2 atoms or electrons in a nonlinear crystal by a pretty good margin. So now I'll show you this animation, which more accurately depicts how it would really work. And you can kind of, again, we color-coded it along a gradient this time. You can see the electrons receiving the waves, interfering with each other, but it's really hard to make out because all you're seeing is a change in opacity. That doesn't really help explain to you what's going on. So this still really isn't a good answer. I'm just trying to build these concepts one at a time. So here's what's really happening, and we really struggled with this one. So we're going to do our best to show it to you, simulate what's going on. Just keep in mind on these follow-up question videos, I try to give my wonderful editor a break so that we're not doing too much work on these. So you can see the emitting electron in the back. It's sending out that wave, and again, it looks kind of straight because it's very, very elongated. It's going to hit these 2 electrons, and what we've done is we're representing a bar going from each electron to the other. And what that bar represents is the amplitude of the wave that electron received. And it's going to send that amplitude to the other electron. The other electron is going to send its amplitude to the other one. And what they're going to get is a time-delayed reception of each other's amplitude that will interfere with the amplitude of the light they are getting. So as the light passes over, and again, it's so much longer, so it's taken a long time to pass. We've slowed things down far below the speed of light here. What's going to happen is that the wave communicated to each of these electrons is actually going to be half the amplitude of the emitting wave. So now we're going to flip it over to the side just to try and make it clear, and you can see the original wave as it passes by the electron, and then you can see the new wave that represents the information that electron is actually receiving because of the interference. It is a little delayed and it is half the amplitude. So this is actually the physical explanation of the beginning of what's going on. Because if you were to say, so Chris, so does this animation represent what's really happening in a nonlinear crystal? I still have to say, not yet. So let me break this down for you, as it is a multi-step interaction that produces the result we see. Step one, a photon wave, which again is very long in wavelength compared to the distance between two electrons, starts passing by these two electrons. Because the wave is so long, these two electrons have time to interfere with each other before that original photon wave passes. That means their interference cuts the amplitude in half. That's one. Step two works like this. Our electrons still move orbits in quanta of energy, and even though the frequency of the light is not changing, the amplitude is, which means half the energy is communicated to the electron. So the electron is not going to jump to an orbit that corresponds to the energy level of the originating light wave. It's going to jump to an energy level that corresponds to half the energy of that light wave. Now, this is what makes nonlinear crystals so unique. In order for the electron to jump to a position that represents half the energy of that receiving light, that energy level has to exist within that atomic configuration. If that energy level doesn't exist in that atomic configuration, there will simply be no response from the electron. So in my first video, I explained nonlinear crystals are so unique because their incredibly tight and symmetrical molecular formation creates the circumstances for this to happen. It is even more unique that the energy level exists for the electron to jump to at half the energy of the receiving light it's getting. So that is the other condition in order for a nonlinear crystal to work. Step three, the electron does not re-emit light as it reacts to the initial light wave. This is another important thing to keep in mind. The electron only re-emits light when it falls from a higher energy level to a lower one. The electron's interaction with the original light wave, all it does is cancel out the light wave with its inverted motion. This is really critical because I found a couple commenters who are extremely passionate about this conservation of energy thing, and they insisted that by me saying that a light wave, this is something I said in the comments, that the receiving electron cancels out the light it receives, it would have to go back and cancel out the whole wave. No, that's not what's happening. It creates a new wave inverse to the one it receives, and that wave expands, and that's expanding while the light wave it hit was expanding, meaning that it just finds its way going back, the light wave goes forward. Because they interact at a certain moment, it's canceled out going forward, it starts to cancel out going back. it can totally progress. It doesn't have to instantly cancel out everything behind it. But that is important to keep in mind for conservation of energy. The final step is the electron falls from the higher energy level, now creating a new light wave. But the reason the new light wave it creates is half frequency, not half amplitude, is because the amplitude is determined by the orbit of the atom, not the originating light wave. So the interference cutting the amplitude in half halves the energy level for the receiving electron. The electron jumps to an energy level half of what it would otherwise. So when it falls down, it re-emits a new light wave at half the energy, which in this case is half the frequency. All of those things have to come together for this to work. And now I need to address two big things. Anyone who is, well educated in quantum mechanics or any of this is going to be screaming at me right now. One, I just used amplitude to describe light. We don't have amplitude in our equations for light. Why do we not have amplitude in our equations for light? We don't have amplitude because it almost never matters nor changes. We use intensity, but intensity, while similar to amplitude, is about its collective amplitude, not a specific photon's amplitude. So I am making a leap and saying, we have to think about amplitude now in quantum interactions with light. Why not? Every other time we deal with light, amplitude is included. The other reason we don't have amplitude in our equations with light is we can't measure it. It's too small. But it doesn't mean it's not there. But the solution is very simple. We just put amplitude in the equation here. And for most of the time, it's just 1, representing a whole original amplitude. And in the case of our electron interaction, the interference causes 0.5, or just our original amplitude divided by 2. Simple. Okay, now, here's another problem. I just mixed classical mechanics and quantum mechanics in the same process. This is basically a sin.
He got
Quantum mechanics,
how much?
classical physics,
He got
classical physics,
in my
quantum mechanics. You see, every element, every material has a spectrum. And that spectrum represents the energy levels electrons can jump to. And so if the only way for a material to respond to light, and of course that's why some things are black, some things are brown, some things are transparent, is because it depends on if there's these energy levels available within how the atom is structured for it to jump to. But every material usually has lots of different levels it can jump to. Maybe you're watching this and it feels like I'm just copying and pasting different things together to make it work. Well, no, but if it feels that way, there is a little bit of backup here. There is a rising star, kind of rock star theoretical physicist. His name is Nima Harkani Ahmad. Forgive me if I'm saying that wrong. And he published a mathematical framework or a theory called the amplituhedron. Here's what this is. He has proposed that instead of, for our different quantum interactions, listing them all out in this just, unending list of Feynman diagrams and trying to add all those up. All quantum interactions can be represented within the volume of this strange multidimensional polytope. It just looks like a really jagged sphere, but it's basically a shape that is just made of triangles. And within each triangle, represents a simple quantum interaction. Now, there's some debate because some people feel like this implies there's some underlying mechanism that is creating this consistency, and some people say it's just an abstract. But if you look at what we've been talking about this whole time with this triangular interaction, and you look at the amplitude-hedron and how that's built, again, out of little triangles that each represent a simple quantum interaction, what you begin to see is that every quantum interaction within a triangular arrangement has this kind of amplitude interference pattern that creates our different quantum interactions. In the amplitude-hedron, the amplitude is considered an abstract representation of the statistical amplitude. And the explanation I just gave you is that it's literally amplitude. So there is evidence that this is actually what's going on. And we've played with other triangles and arrangements, and we found that you can get all sorts of different kinds of outcomes with one side canceling out completely and it just changing the direction of the wave, producing different kinds of frequency arrangements. This is what I meant when I said this is a big rabbit hole that I'm just going to dip our toes into, because it would take years of work, and it is going to understand every quantum interaction well enough to from that high scientific standard, put a stamp and say, all right, we know that this is real, and there's this variable of amplitude that we have not been including in our consideration for quantum interactions. And I'm not here to do that. I am simply trying to give you a physical explanation that is plausible enough for you to understand that, as with everything else I cover in my science videos, we don't have to have magic. We don't have to have mysticism in this. There is a geometric, physical mechanism behind everything that happens in our material world. And we can find it if we just look hard enough and don't throw up our hands and say, I guess thought creates reality, and it's a flip of the coin multiverse. But bringing this back to just light for a second, any interaction between 2 points within a triangular arrangement means that the waves produced will have some kind of interference pattern that is reliable, that ends up outputting the exact same amount of information as was input to it. And that's pretty cool. Those of you guys out there that do computer modeling, that love dabbling in simulations, take this idea and run with it. I've just given you the framework for how to do it. Have fun. If the two interactions are not in a triangle, if they are on opposite sides of each other, or if they are hit simultaneously but too far apart to interfere with each other before the full photon wave passes, then what happens? Do we get more light? Yeah, we do. That's what's kind of cool. We don't get infinitely more. We don't get, it's not infinite energy, because again, we're kind of limited. We're still limited here. And if they're on opposite ends, they can never really interact with each other to constructively interfere in such a way as to produce an even greater effect, because they're on opposite sides. They'll never come back and meet in the middle. I'm not telling you anything that gives us infinite energy, but it does say maybe there's more energy in a photon than we originally thought. Yeah, also fine. Is there evidence of that? Yeah, there is. So just like scientists had nonlinear crystals, which they struggle explaining, we have also discovered crystals that amplify light and actually put out more light than we put into them, or put out more light than we think we put into them, would be more accurate. And they're called, which is so depressing, photonic time crystals.
You failed!
Yes, we called them that. They think it has to do with time. It's so frustrating. Anyways, I linked to it in the description. You can see it for yourself. They're not time crystals, people. It's all geometry, okay? We don't have crystals going back in time. But anyways, that's the reason I'm doing this series. Take the madness out of this shit. Okay, but look, even if you need maybe something a little more familiar to make you feel better about all this, here's a list of equations here. We have the Euler-Lagrange equation, we have Gauss's law, and we have the principle of least action. All of these equations are communicating a very similar thing, that these EM interactions, these physical interactions, all balance out. And they do so through physical mechanisms. And, Veritasium did a whole video on principle of least action where they said this is probably the closest thing to a theory of everything we've ever gotten to. And in that case, I mostly agree. This is, at least in principle, the underlying root of all physics. That the energy is conserved, but the conservation isn't magical, it's a physical mechanism. Now, that I said I agree with Veritasium on that, now let me completely dump on them. So, another objection that was brought up to light, and this is all related, being a photon ring, is the idea that in quantum field theory, light travels all paths at once, and basically just we experience the path of least action, but light explores all possible paths for any given interaction. No, that's a mathematical construct, and again, math does not create reality. But at the end of this video, they did an experiment that they said proves this is true. So some people brought this to my attention. They want to know how do I explain this? Well, so first of all, again, if the photon is a ring, it's not traveling all paths at once, but it does travel quite a few. But no, it doesn't travel everywhere at once. So at the end of this video in Veritasium, they show an experiment. And I'm going to read you a letter sent to me by one of the optics engineers who's helped me out. Now, he's asked to remain anonymous still because he's not interested in hurting his career by being part of this crazy stuff here. And you can believe me that this is actually from a real, we're talking PhD, fully qualified, traditional, works in the field with light every day. Obviously, because I have to keep him anonymous, you don't know if I'm telling you the truth or not. So all I will say is when I read this to you, if you're an optics engineer, I'm sure you will recognize the language. So at the end of the video, they shine a flashlight on a mirror with a diffraction grating nearby and a camera near the angle of reflection to the image of the reflected light. When they partially cover the mirror with black cardboard and shine the flashlight off the specular path, they claim it's evidence of increasing the probability of a certain subset of all the possible paths of light could take. They even point out in the video that it's a sloppy experiment given how unculminated, diverging in this case, a flashlight is. So they attempt the same experiment with a laser beam and claim that the increased collimation or directionality of the beam means that the light falling on the diffraction grating must be taking one of the possible indirect paths to get there. The issue in their interpretation of the laser beam results is that it ignores the diffraction at the laser aperture itself. The beam, while well collimated, is still spreading over 180 degrees as it leaves the cavity. It's just a very small percentage of the total light. All you're seeing in the video is that the higher order diffracted light being diffracted again by the grating and sent back into the camera aperture. That's why they have to get close to the edge of the black cardboard to make it work. If they were truly trying to demonstrate all possible paths where traveled, then it wouldn't be hard to construct a version where the diffraction grating could be placed much farther from the beam and the light could be directed back into the camera. But they didn't show it because it doesn't happen. They took effects that were well explained classically and grossly misattributed it as definitive proof of the physicality of Feynman's interpretation of quantum mechanics. So if I were to say that more simply, light's messy, okay? Even a laser beam, you can go get a laser pointer, and it looks like that really precise red dot. What you are seeing is an effect of coherence. It's the fact that there's so many kind of crazy light waves in one place that it presents to us this illusion of consistency. But even with a laser, even with some of the best lasers on the planet, if you were actually to zoom in and inspect the various wavelengths, you will find that the color that you see is actually just an average out of many different spectrums of light within it. Because light, it's just so hard to get it perfect. And that's also why the world of lasers is such a big investment. And we're always trying to figure out how to improve them, make them better, and increase the coherence, because getting a perfectly coherent beam of light is really, really hard. Certainly not something you can buy for even $100, off Amazon. So this is like one of the big things in optical engineering is coherence. So Veritasium is fooling you with your assumption that the laser is this neat, tidy beam of light coming out, when really it's already shooting all over the place. Not because light's finding all paths at once, but just because it's messy. And just as a quick side note, Veritasium is not one of the science communicators that has been on my shit list. And I do have science communicators on my shit list. But the last couple Veritasium videos have gotten me worried that the guy's diving into this whole, like, I'm on this, quantum weirdness string theory bandwagon now, and I'm just sitting here trying to justify crazy ideas. It does worry me a bit, bro. Come on. Come back to the good side, please. Okay, so all of that coming around, waves don't collapse. Mathematically they do, because we start with a probability, we detect it, and then we move from a statistical equation to a linear equation. Fine. What's really happening in reality, an EM wave is created and it just keeps going. It disperses as it grows. It gets canceled out at various points. It's like raindrops in a pond. And this just, this is our world. This is the world that we live in. Just messy EM waves all over the place, everywhere, all the time. And it's conservation of energy is not a problem, because we have this geometrical separation, and when we get too close, we have interference. We have that conserves energy, or things just get too far apart to work together anymore. It's all there. We don't have to worry about it. We don't need magic to make the world make sense. Let me answer a few other questions that I've gotten since I made the video. One question I've gotten is, if you're right, if light's just an EM wave and the wave is expanding, how does the light from stars reach all over the vast distances of space to get here? It's a good question. So the first part of the answer, it's really technical. Stars are really fucking bright. Like, just mind-bendingly, inconceivably bright. I mean, let's just soak that in for a moment. Have you ever looked into how far away the sun is from us here? Like, have you ever just researched that? There are great videos on YouTube that like show this stuff to scale. Like, here's more realistically how small the Earth is, how big the sun is, how far away from us it is. And even with as far away from it is, it's literally frying the planet. I mean, that's partly our fault too, but still, it's happening, okay? Stars are really bright. So just right off the bat, that's one answer. All right, now to the second group of people who, talked about how, they feel like if they look at the math and, there's no way if light's an EM wave, it would be able to last. It would disperse too far over that distance from the stars to the Earth. You're probably confusing near field interactions with far field interactions. Yeah, so near field interactions disperse at 1 over r to the power of 4, but far field interactions disperse at 1 over r to the power of 2, which that's a pretty big difference. So, yeah, and then again, stars are really bright. And that's one of the things that just, it's a little frustrating to me, and that's why I'm doing this series. We think we look at these math equations, we think they're rules. They're not, they're descriptions. And we need to understand what it's describing when we look at the math equation, because it may not be describing the thing you think it's describing. Someone asked, then if light is just an EM wave, why is it affected by gravity? Well, because EM waves move through space, and gravity is about space getting fatter. If you want more details on that, go see the first video in my series. Oh, I love this one. I kind of compiled this together. The criticisms of my video are, this is just quantum field theory and you're taking credit for it. Then you're misrepresenting quantum field theory and you're wrong, quantum field theory says so. And I think the inconsistency of all of these statements shows just how difficult it is for anyone to understand quantum field theory or come to an agreement on what it means. But y'all might want to get together and get your story straight before you make your declarations. Which is it? Am I just showing quantum field theory and taking credit for it? Or am I misrepresenting quantum field theory? Or does quantum field theory something completely different that proves me wrong? You guys can figure that out all you want. Now, to answer that a little less sarcastically, where does quantum field theory fall into what I'm presenting? Yeah, some of the math in it is good. Almost all of the inferred underlying mechanics are wrong. And the extrapolations that we've made from the theory, I think, are crazy. So yeah, I'm not a big fan in the end of all of that. This is my favorite silly outcome of quantum field theory. And this goes back to another question. Let me just address this for a minute. A lot of you keep saying, okay, light's an EM wave. What's waving? All right, I know what you guys want me to say. And there's a reason I haven't said it yet. I'm going to say it just this once for this reason. So quantum field theory is what we use to replace the idea of the ether. And the ether is the idea that space is all made of some kind of substance. And I see physicists all the time, oh, it's such an archaic theory. We have a much more enlightened theory now. It's quantum field theory. And in quantum field theory, space is made up of lots of different fields. How is that different? More importantly, how is that better? Ether's primitive because space is made of one thing, but the enlightened version is space is made of lots of shit, just all stacked on top of each other neatly? Nah, it just doesn't run well with me. That's weird. Now, am I saying I think it's ether? I'm not saying it, but I'm not saying it yet. All right, so let me wrap this all up. I tied a lot of concepts together, basically trying to explain to you that the wave doesn't collapse. It doesn't need to. We have other processes in place to conserve energy. They're all geometric, of course. In this case, mostly triangles. Locality is not an issue because we can give them time to communicate. That's fine too. So there's still nothing really spooky going on here. But there's a slew of questions I just want to kind of bring all together here. And I guess I would just kind of describe it as kind of if the light hits and nothing happens, where does the energy go? All that stuff. So if we go back to the beginning of the video where I gave you that idea of the magnifying glass burning a leaf or an ant, it's not the light you see, it's the light you don't see. So here's the thing. Electrons aren't the only thing that move. A good way to think of it is like if the room is available, like when we talked about polarizers, if the room's available for an electron to move, it will move because it's the smallest mass object in an atom. But if the electron can't move, but there's still an electric field imbalance, well, then the rest of the atom moves. And so, for example, a proton is the protons and neutrons at the center of an atom are heavier than the electron. So when they move slower. And that's why a lot of heat is infrared, because we have visible light hitting, the electrons can't respond to it. So the rest of the atom responds to it, and it does it much slower. And, I think all of you know from childhood science videos and everything, we know that heat is vibrating molecules. There's this whole world here, again, of just EM waves waving, things responding to it, everything's constantly moving. It's literally what keeps our world alive. It's what gives us heat. It's what determines kind of how things interact. And I had a couple other people mention this. This also answers the idea of like quantum foam, particles popping in and out of existence. If the universe is just full of everything waving and everything's responding to the waves, making new waves, and it's just all over the place and the EM waves never really die, they're just always out there being canceled out or not, then it makes perfect sense that if we zoom in at any particular tiny point in space and look at it closely enough, we're just going to see errant waves randomly, constructively interfering or destructively causing what we can detect as particles theoretically popping out of nowhere. It's not because a particle is literally appearing or disappearing, it's because a wave interaction that we can detect appears for a second out of the randomness and the noise, and we go, ooh, I saw something, and then it goes away. But again, it wasn't even a particle, just an EM wave. It just happened. And when you get a universe this noisy, you're gonna get that. This is a very fun world to explore. For a lot of this, I don't feel like I'm the best person to explore it. I think there's people that do a very good job talking about light very well. Again, I linked to 3 blue, 1 brown in my last video. I am here just to lay out breadcrumbs of concepts so that when we get to the final video, you have all the concepts in place to not just hear the ultimate thing I'm trying to bring out, but that you yourself feel like at that point it's almost obvious. Like think of it, it's like a murder mystery where all the clues are laid out and 5 minutes before the detective tells you who did it, you figured it out because all the clues have been laid out. That's what I'm trying to do with this series. So I don't care if you believe me. I don't care if you think this is true or not. My target goal is interested but skeptical. That's where I'm hitting to. I want just enough plausibility to keep you interested. Perfectly fine staying skeptical. Finally, it's just to know, a lot of you have reached out. You've sent me stuff. I want you to know I read everything you guys send me. Again, I have a living that's not this. I am trying to work on that. More on that in a minute. But this, if I haven't responded, just know it's either because you just sent me too much. There's just no way for me to read through your whole science paper. I'm sorry right now. But I will try as best I can to include everyone in communications as we grow. Again, as a reminder, before this and the next chapter in the series, because the next chapter is going to take a really long time, I'm going to be doing videos on some other topics. The next one is on free will. I hope that piques your interest. Oh my gosh, you made it this far into the video. That means you either fell asleep watching. You know what? I do see a little drool right there. You know what? I'll leave you alone. Or you're one of my more enthusiastic followers. So here's what I wanted to talk to you about. I've gotten a lot of feedback and input from people recommending that I do a Patreon page. Obviously, I get a lot of people asking me to do more, do my videos faster, get more videos done, do other topics. And of course, I want to do that. Here's my big problem. Well, I have 2 big problems. The first one is I'm very uncomfortable taking people's money without feeling like I'm giving a good value in return. I'm very happy taking YouTube's money, of course, because, it's YouTube. But even then, most of that money goes to my daughter, who is not just my editor, she's my accomplice, and I couldn't do these videos without her. As a matter of fact, in many ways, she's smarter than me, and it was actually her idea in this video to incorporate Amplitude to solve the nonlinear crystal problem and conservation of energy and all that. So the second problem I have is just making the leap. Again, I'm fully employed. I'm taking care of a family. I have been working for the past year to lower my expenses to make it the leap as close as possible, but it's still a pretty big leap. So I've put a survey form on my website. The link here is shown below, and it'll be in the description, www.christhebrain.com/Patreon. Again, this is just a survey here to test the waters. After years in marketing, and I'm sure many of you realize, most of these numbers are complete BS. For all I know of my 25,000 subscribers, most of them are bots or possibly the NSA, who knows. So please go to the forum, let me know you're real, let me know how much you'd most likely be willing to support. Please be very, lowball it. Because this is a way for me to test the waters, and let me know what you'd want to see from me for that investment to give back. And of course, there are so many things that more things I want to do. I do have, dozens of half-draft ideas and half-written scripts, articles that I want to finish up for my videos for people who want to get a little more deeper dive into it, into the math, into the research. All of these things I really do want to do. It's just with the time constraints I have, the videos seem to be the most effective thing to spend my time on. So all that being said, again, please just fill out this survey, let me know. And then the other news I just want to have today is that you should see dropping here within about a week or two at most, a thumbnail previewing an upcoming live Q&A that I'm going to schedule. It'll be for you guys to ask me anything you want. Can be the science videos, can be other things, can be, what's up with the beard, anything you want. I'm looking forward to that as well. So again, I appreciate everyone's support. Thank you very much, and I hope everyone gets some good sleep and keeps learning. The outdoors is loud.